Someone knows. What's a secant line? When it comes to a circle. That'll be your hint.
When it goes through two different.
One over.
When it goes through two different times. So like in geometry, you said you had a circle and a secant went through 2 times, and that was the geometry definition of a secant. Well, a secant actually is something we have in a function, and a secant in a function is going to be a line defined by 2 points. It might go through more than once, like this one you can kind of see it goes through 3 points, but it is going to be a line that hits the function twice. And what is important is often being able to find the slope of a secant. The slope of a secant line is just your regular old school slope formula you learned in Algebra 1. So we know that we have the change in y over the change in x. Hopefully you remember that formula. In calculus, we tend to write this a little bit differently. We'll write it as f of, I'm going to use different letters here. In calculus, we tend to write it like this, if I can get there. F of b minus f of a all over b minus a. But again, that is just slope. And oftentimes we use the lowercase m to represent slope. Where those are coming from, so I'm just calling generically, one of these points would be at a comma f of a, where f of a is the y coordinate. The other point is at b comma f of b, where f of b would be the y coordinate at b. So that's what we call a secant line. It has a slope. That slope we can find. The idea behind calculus, though, is this thing called a tangent line. And this is really where calculus, like almost all of calculus, relates back to this thing. And in calculus, we're concerned about, well, hey, I can draw a tangent line. Which, what is a tangent line? It is related to the tangent line you learned about in geometry. In geometry, a tangent line is a line that touches a circle exactly once. It is perpendicular to the radius. For calculus, a tangent line is going to be a line that brushes up against the function in one spot. It might cross later if the function bends a lot, but it's going to be tangent to that function. The point where it hits the line is called the point of tangency. And things in calculus are always kind of going back to this point of tangency and the tangent line. And what calculus is kind of asking is, how can you find the slope of a tangent line? So we can easily find the slope of a secant line because we clearly have 2 coordinates and we know slope is the change in y over the change in x. But when it comes to calculus, we often want to figure out, well, what is the slope of that tangent line going to be? And we can actually find the slope of the tangent line using limits. And I'll show you how we find the slope of the tangent line in a second. So first off, let's talk about what the derivative is. So if you don't pick up anything else today, I want you to know what the derivative is. And the derivative for us, we're going to say that the derivative of a function f at some x coordinate, and I just picked kind of x equals c, is the slope of the tangent line at c. Well, what do I mean by that? So I have some random function. I'm going to call it the function f of x. I have a tangent line drawn. The slope of this actual line at the point x is equal to c is literally called the derivative of that function. So in the most basic terms, when I say things like derivative, if I can spell derivative correctly. When I say derivative, I want you to think of slope. The derivative is nothing but a slope. It's a little bit different from like the old school slope you learned in Algebra 1. instead of being a slope between 2 points, it is the slope at exactly 1 point, which is what kind of makes it useful. And the idea behind being able to find the slope at a point has tons of applications, which is what we basically spend some of this unit on, unit 3 on, and unit 4 on. So kind of go hang in your head, when I say derivative, I'm talking about the slope of a tangent line. So the first thing that we need is we do need to have some notation to talk about the derivative. So we know that mathematicians love their symbols. When it comes to having these symbols, we want to make sure that we can talk about calculus correctly and just use it appropriately. We don't have to write out the word derivative every time. So up here we have, obviously you can tell these are some old men. These are considered some of the founders of calculus. Calculus was of course founded in other, it was known to ancient civilizations, but being Europeans, they claimed it as their own and kind of put their names on it. And we have different notations that we will use equally. So Sir Isaac Newton, most of you have heard of him before, dealing in science class, but he is considered one of the fathers of calculus. We have Leibniz. He also is considered a founder of calculus. Him and Newton kind of discovered calculus around the same time. And then we have Lagrange, who worked in calculus a little bit later, but we also have his notation as well. The Lagrangian notation is one of the more common notations we use. And the notation we're going to use for the derivative is going to be written as f with an apostrophe of x. How you would read that would be something like f prime. So when you see that apostrophe, you're going to read that out loud as literally f prime. The Leibniz notation, it also can be representing as the derivative. He wrote his derivative as dy dx. It looks like a fraction. We're not always going to think about it as a fraction. We're going to think of that as its symbol itself. How we read that one out loud is we literally pronounce that to ourselves as dy dx. So no one really often says dy over dx, but when you say dy dx, that is what we mean. F prime is how we say the Lagrange. Those are the main two ways we will represent the derivative in this class. Those symbols are interchangeable. Newton also had a way to write it. His kind of looks like the Lagrangian way, but he used a dot over the variable y. We don't really see that when in modern terms, like we typically look at the Lagrange notation and the Leibniz. And then we're often looking at the derivative at a particular value. So if I can say something like, hey, what's the derivative at 2? You could write something like f prime of 2. And how we interpret that is the slope of the tangent line when x is equal to 2. The Leibniz way, we can also show what that means. The Leibniz notation is written as dy dx, and it has a vertical bar, x is equal to 2. Leibniz is a little bit more clumsy to use when you're plugging it in. It has its own applications. So for the most part, you'll see me using the Lagrange notation, especially in this unit. But do know that Lagrange and Leibniz, those notations can be used interchangeably. Any questions so far?
Yeah, what would Newton's look like?
Newton's, he wrote it the same way. You can use parentheses, and he would write it like that. And you would pronounce that as y dot. But we won't ever see that one really in this class after today. So let's go back to, like, how are these derivatives coming about? So there are two official definitions of the derivative. We have what's called the alternate definition of the derivative, and then we also have what is called the traditional definition of the derivative. I'm doing the alternate one first because to me it's a little bit easier to understand. And the alternate definition states, so if you want to find the derivative at a point, so that's what I have up here, f prime of 2, what that literally means is the derivative when x is equal to 2. And again, when I say the derivative, in your head you're just thinking, okay, that just means the slope of the tangent line. And where the derivative comes from in the alternate definition is this equation. I'm going to write it down first and then explain it. But it's going to be the limit as x goes to 2 of f of x minus f of 2 all over x minus 2. And you might look at that and you're like, Mr. Brown, that looks very familiar. And I go, I hope it does, because I gave you questions in Unit 1 that were in this format. You didn't know at the time, but you were actually finding derivatives using that limit question. So let's think about what this actually means. If you take away the limit part of this, it looks like an old school slope formula. So we have just f of x minus f of 2 over x minus 2. And this looks like an old school slope formula. And when I say old school slope formula, we have some change in y over the change in x. And we know that's where slope itself comes from. Where this is coming at to be a derivative, when we see a variable in math, we know that that is something that is unknown. So one point that is definitely true is we have one point on here that is at 2 comma f of 2. That is a known point we have on the graph. But we have this other point that is unknown, and we're just going to generically call it, well, whatever x is, comma f of x. And if we connect those 2 points right now, they would be considered not a tangent line, but a secant line. By adding the limit here, I want us to remind ourselves what the limit means. The limit as x is approaching 2. So what that literally means is this x coordinate over here is approaching the x value of 2. So think conceptually what's happening. As that point, the one that I've called x comma f of x, as that point is literally moving closer and closer to the x value of 2, what is that orange secant line going to eventually line up with? Any ideas, if you can kind of see it?
Could you repeat that?
What's going to happen as this blue point at x comma f of x approaches the x value of 2? So I'll draw it in. So let's say it's moved one step closer, so now it's over here. Here's the secant line. It moves a little bit closer. Here's a secant line. What is this secant line going to eventually become when that point hits the x value of 2?
The tangent line?
Tangent
It's
line.
going to become the tangent line. And that's kind of a very like theoretical, conceptual thing. But basically what's happening is we're taking the slope formula that you learned in Algebra 1, and we're saying, well, what if these 2 points, instead of being separate, they actually merged into a single point? And that's where we get the slope of the derivative from. And so I want us to think about when we see this limit expression, that means the slope when x is equal to 2. We also have, and I'll take questions on it when I finish this part, we also have the traditional definition of the derivative. It works about the same way. It's where you still have 2 points that are forming a secant line. One of the points is known, so we're going to call it 2 comma f of 2. The other point we don't know, but the gap between the 2 points is h. So you might see where this is kind of headed. Well, if we're starting at 2, this x coordinate will be 2 plus h later. Its y coordinate would be whatever 2 plus h is. So if I want to find the slope of that secant line, I have the change in y. So there's my change in y over my change in x. Well, for my change in x, one of them is at 2 plus h, the other one is at 2, which is just going to give me h. That's the difference between them. Well, if I want this secant line to become a tangent line, what is my limit going to need to be? How can I make those 2 points become the same point?
As x approaches 2.
So x is approaching 2. In this case, we're calling it 2 plus h. So say it in terms of h, what value do we want h basically to become? if we want this point to merge into the other one, that value of h is going to go to what number? Where h is the gap between the 2
2.
points. Say again, Armani, I think that was you.
I said f of 2. Or would it just be 2?
Asking a good way. I'm just gonna go ahead and tell you. The limit as h goes to 0 would be the derivative we have there. So I want you to kind of see what that means. If the h is going to 0, the gap between the 2 points is going to go to 0. Well, this gap is going to 0. This point's getting closer and closer. So eventually when h is 0, it's the same point, and instead of having a secant line, we now have a tangent line. Some of you are like, Mr. Brown, I am completely lost on this. Like, I do not know what is happening here. And I kind of want to leave it vague as like, it will make sense eventually. Like, some people are very visual and it clicks automatically. Some people, they do need to see kind of practice. If anything right now, I want us to understand that when we see this statement, this means the same thing as the derivative, the slope of the tangent line. Same thing for the alternate definition. If you see something that looks like this, we interpret this as the same thing as the derivative at 2. So instead of worrying about the notation, let's just talk about like, well, what the heck does this thing about the derivative mean, and how can it help me do different things? So this is probably the most important slide that we're doing today in our notes. And if you're looking at this, I have the sign of the derivative. So the derivative can be positive, it can be negative, it can be 0, and then we also have some weird cases of where it's not defined. So first off, to make sure we're all starting this slide on the same page, when I say derivative, what's one word you can use to summarize the derivative with to help us think about this question?
Slope.
Slope.
Slope. So we know that derivative is slope. So if I say f prime of c is positive, another way to think about that is the slope is positive. Well, if the slope is positive, what is the graph going to be doing?
Going up.
Going up. So we have f prime of c is positive. This means that f is increasing at x is equal to c. Likewise, if we say the derivative f prime of c is negative, we know the derivative means slope. Well, if f prime is negative, what is the function doing at that value?
It's going down.
It's going down. And we're going to say f is decreasing at x is equal to c. And then let's pull that together. Well, if I say the derivative is 0, that's another way of saying that the slope is 0. What would it mean if the slope is 0?
A straight line.
It's a straight line, particularly not a vertical straight line, but a horizontal straight line. And we're going to describe that as f has a horizontal tangent. At x is equal to c. So what I have underneath this is I have a graph, and we're going to find one x value. There's lots of different answers, but we're going to find one x value that would have a derivative that matches. So in that first column, we say f prime of c is positive. We know that when the derivative is positive, the function would be increasing. What would be an x value on that graph that would have a positive derivative? Which also means where on this graph is it increasing?
Four.
4. So if I just look at 4, the graph is increasing at 4. So we know that the derivative at 4 is greater than 0. Another way to say that is I can just say f prime of 4 is greater than 0. If my board would work. There we go. And again, you can kind of imagine, like if I drew a tangent line at 4, like there's a little baby tangent line, it does have a positive slope. This second column, I say that f is decreasing at x is equal to c. So if I wanted to write a statement, f prime of what is less than 0? What would be an x value that would have a negative derivative for this one?
2.
2, 1 would work, 1.5. I'm gonna choose 1.5 just to be different. Anytime you're decreasing, that will have a negative derivative.
So we
And
can
then
use
we can
difference.
also have a derivative that's equal to 0. And that's going to be where the graph is pretty much not increasing or decreasing. It's where you have a horizontal tangent. What would be a location on this graph where the derivative is equal to 0, do you think?
3.
3.
3. You can kind of imagine if you draw a tangent line here, that tangent line has a slope of 0, so f prime of 3 would be equal to 0. And that has tons of applications. In this unit, we're going to keep it straightforward and just talk about when is the derivative positive, negative, or 0. But we'll see as this year progresses, that has lots of different applications and a lot of different contexts. And then we have this fourth column. These are where there is no derivative. And you do need to kind of know these cases. The first case is if the function has a discontinuity, there will be no derivative there. And that kind of makes sense. If the derivative is a slope at the tangent line, if the graph doesn't even exist there, it can't have a tangent line there either. So any discontinuity, so whether you have a hole, a jump, or a vertical asymptote, there is no derivative at that location. We also have a case where there will not be a derivative. And mathematically, it's defined as if there are different left and right tangent lines. Visually, we're going to call this if there is a cusp on the graph. You can interchange cusp with the word corner. And you're like, Mr. Brown, what does a corner look like? It could literally look like a corner on the graph. So if you have a graph that has a sharp point, there is not a derivative at that sharp point, so kind of like an absolute value function. It wouldn't have a derivative at the vertex. It could also be curved. So if you think of like, I don't know, that bird shape everyone drew in elementary school, at that sharp point, there is no derivative either. We also will not have a derivative at a vertical tangent line. So if I think about a function with a vertical tangent line, at the spot where the tangent line is vertical, it will not have a derivative. And I think that makes sense because back in Algebra 1, you learned that a vertical line had an undefined slope. Well, if we say undefined slope, we're also going to say that the derivative is not defined either because the derivative is just the fancy way of saying slope. Questions on that slide? That's definitely the most important one we have to look at. All right, so some examples. I have a random graph up here. That I definitely, it's just the graph of f. And underneath it, I have 4 statements that we're going to answer in terms of the graph. Some of these are going to be asking for the value, some are going to be asking for a secant line, and some will be asking for a tangent line. And then we'll just kind of talk about whether it's positive, negative, 0, or not defined. Your homework tonight is just like this page. But a few more problems. So this is kind of going to model what the homework does, kind of focusing very more on the conceptual aspect of this thing called the derivative. So first off, looking at these 4 choices, and we're thinking about the rows, first row, second row, third row, and fourth row, which ones of these are going to represent a derivative? We'll start there first. And how can you tell? I will do it this way. We're going to say yes or no. Would this first one, if I just say f of -3, would that represent a derivative?
No.
No. What is f of -3 representing? If you're looking at those 3 options, is it a value? Is it a slope of a secant line or a slope of a tangent line?
It's a value.
Value.
It's just a value. And we'll come back and fill it in a second. This second one, I have f of 1 minus f of -2 all over 1 minus -2. Would you say that that's representing a y value, a secant line, or a tangent line? And how can you tell?
The secant line.
The secant, clues that you know is a secant. It looks like the slope formula, change in y over the change in x. How do we know that the second one is representing a secant and not a tangent?
There's no limit.
There's no limit expression in front of it, which kind of then is going to answer what comes after it. Again, not every limit is going to be a derivative. It's only limits that are in either the alternate definition form or the traditional definition form. So the second one, this is the limit of an old school slope formula. So this one would be the slope of a tangent line. This third one, this is kind of like the plus h version. This is what we call the traditional definition of the derivative. It is a limit, so it's also representing a tangent line as well. So let's go in and fill in some of these blanks and answer the questions just to kind of pull it all together. So we already said that f of 3 is representing the value. Is it too small if I make it look like that? Can y'all still read it?
It's fine.
Sure. Okay. So if I say f of -3, that is just the y value when x is -3. -3 is right here. So if you wanted to classify that as positive, negative, 0, or not defined, what would you say f of -3 is?
Positive.
0.
It's 0. And we know that it is 0 because it's on the x-axis. The second one, though, we might need to think about it a little bit more. So this is the secant line. We know the secant line connects 2 points together. Based on its format, I see it's going from when x is -2 to when x is 1. So if I draw that in from -2 to 1, there's my secant line. Would you say that that value is going to be positive, negative, 0, or not defined? And what would be your reasoning when you answer that?
Negative.
It's negative. Why? Because the secant is decreasing. And we know that a decreasing secant means that the slope of it is negative. This last one, or not the last one, next to the last one, is a tangent line. I see f of 2 there, so this is the tangent line at x equals 2. So looking at 2, I can kind of estimate what that tangent is. It looks like this. Would you say that that tangent line, the derivative, so would the derivative be positive, negative, 0, or not defined?
Negative.
Negative.
Negative, and how do you know?
Decreasing.
Because f is decreasing at x equals 2. Again, another thing that I want to kind of emphasize to us, so that whole limit expression and why we like kind of having notation, this limit expression could have just been written a lot shorter if we just said f prime of 2. Those two statements are exactly identical. One's like the limit definition of the derivative, the other one is just the notation of the derivative. And then we have this last one. It's the limit with 3 in there. So this is the derivative at 3. Another way you could have written this problem is to literally write it as f prime of 3. So going back to my graph, what are we going to say about the derivative at 3? Is it positive, negative, 0, or not defined?
Not defined.
Not defined.
Not defined. If I asked for a reason, what would be your reason that the derivative at 3 is not defined?
There's a corner.
There's a corner or cusp on the graph. And again, we can use those words interchangeably. So I'll say something like because f has a cusp. Again, you can also use the word corner. They're interchangeable at x is equal to 3. So that is the most kind of basic idea of what we have for the derivative. I know today's notes were a little bit longer, but there were just certain things I needed to get out to you before we start doing some more with it. Tomorrow, we're just simply going to build on this idea of the derivative, like still reinforcing like what does it mean when it's positive, when it's negative, and different things. Your homework assignment is in OneNote. It's called Definition of the Derivative. To show you a little bit what it looks like, it's basically just like that part of your notes. So on the front, I give you a graph. On the front side, I have you circle like which value is greater with like a short justification of your answer. Some are derivatives, some are secant lines, some are values. Then the back page looks just like the notes. So I give you something, and you tell me whether it's positive, negative, 0, not defined, and then a brief justification. I don't think this homework takes you too long, but again, this homework is also super important because this first homework lays the foundation for the rest of the unit, especially what we're going to start doing tomorrow. We actually have to graph a function based off of provided information about the derivative. So that is where I'm going to go ahead and end notes. Mitchell, I see your hand. If you're good to go, then you can go ahead and sign out, and I'll see you tomorrow.